My name is Rebecca Nunu, and I am a scientist at Southwest Research Institute, located just down the road here in San Antonio, Texas. I'd first like to start off by thanking the Texas Alliance of Groundwater Districts for the opportunity to speak here about some recent work I've done. I'd also like to thank all of y'all for being here today. This work has been started in 2019 as a small seed grant with Big Bend Conservation Alliance, and ended up being the topic of my master's thesis, which I recently defended in December at the University of Texas at San Antonio. And so with that being said, the title of my talk is The Application of a Geochemical Framework to Characterize Complex Aquifer Recharge-Discharge Relations. And so, increasing water demands and limited supplies are presenting severe challenges to sustainable development in many parts of the world. I think we can all agree that this has been a common theme of many of the talks we've listened to here at TAG. And so, taking a long range at our water supply is more important now than ever before. Pictured here is the US Drought Monitor from 2011. The drought in 2011 was said to be the worst period of drought in Texas over the since 1895, and that's clearly depicted here, as Texas was pretty much all characterized by exceptional drought intensity. And so 12 of the 15 fastest growing cities in the US are in semi-arid and arid regions, largely in Texas and the US, or in the Southwest. So our population is growing predominantly in areas that are already considered water stressed. Let me fix this. So, changes in climate are going to cause less precipitation that will shift precipitation zones to the east. And so, given less recharge and more evaporation, groundwater resources are expected to pick up the slack of meeting our growing demands. And so while water conservation and efficient water use are powerful tools for reducing water demand in many communities, these measures cannot address all needs. So effective groundwater management requires that the hydraulic recharge-discharge relations that manifest at springs be understood well enough to assess impacts of changes in recharge and/or groundwater withdrawals. So applying a geochemical framework can be a really useful tool in water resource management because it can highlight subtle differences in flow regimes and flow paths that are not easily discernible using other methods, such as potentiometric surface mapping or dye tracer tests. This is especially relevant when you're dealing with a very complex geologic environment that have very similar rock types. So a geochemical framework is a structured approach and tool that's employed as a workflow from data collection to interpretation from a geochemical perspective. So in the application of a geochemical framework in this study, it includes field data collection and synthesis of both historical and contemporary data, the implementation of different tools such as statistics and modeling, as well as refined interpretations of hydrologic systems. And in doing so, the application of this geochemical framework can elucidate sources of recharge that manifest as discharge in springs, evolution along flow paths, or water host rock interactions, and spatiotemporal variability in spring discharge. In this study, we focus on San Solomon Springs, which are a series of springs in semi-arid West Texas. If you've been to Balmorhea State Park, you've swam in the largest spring of this spring system. And so infrastructure growth, agriculture, and unconventional oil and gas development all growing demands that impose a greater demand on to meet our needs. San Solomon Springs, as I mentioned, is located in West Texas in the Trans-Pecos area, right here where the star is. So San Solomon Springs consists of 6 different springs and is considered a multi-outlet spring system. And those 6 springs include Phantom Lake, Giffen, San Solomon, Saragossa, East Sandia, and West Sandia Springs. And collectively, these springs are important because they provide habitats for federally endangered and endemic species and are used to meet irrigation, recreation, and municipal needs. As pictured here, the San Solomon Spring system is situated in a very complex geologic environment. We have many of the same rock types as well as large structural features that impact flow. And so previous studies have focused on this area and have laid the groundwork for the work that we're doing in this area. Namely, there is a proposed flow system that originates in the Wild Horse Flat and emanates along in this general direction along fractures and faults to meet the springs. There are also local flow paths that contribute to spring flow that collectively all meet the springs. But what's important to note is although this was a very substantial contribution to our understanding of this geologic area, it did not provide an explanation for the source area for all 6 springs of this spring system. And this conceptualization was formed close to 20 years ago, so it warrants an additional look with new data and more geochemical data to refine our conceptualization of this spring system. So with that being said, the objective of this talk is to investigate the hydraulic relationships among the individual springs of the San Solomon Spring system using a geochemical framework. And in doing so, we hope to answer, do different local or regional sources contribute to all 6 springs of the San Solomon Spring system? So, our technical approach begins with the collection of an expanded suite of geochemical markers. We don't need to get too much into the nitty-gritty, but we've included physiochemical parameters, which are things we collect in the field, such as temperature, pH, conductivity, a large array of ions, including our major ions, trace elements, nutrients, and a large suite as well of isotopic data. Our technical approach also includes field data collection in the study area. We collected samples from all 6 springs and 3 nearby wells in order to refine our conceptualization of this hydrologic system. And as you can see, we have Phantom Lake, Giffen, Saragossa, East Sandia, West Sandia, San Solomon, and the Davis Mountains. So, in addition to field data collection and data synthesis, we can then apply geochemical and multivariate statistical methods. So we'll start off with major ion composition. And depicted here is a Piper plot, and this is a pretty conventional way of viewing geochemical data and establishing hydrochemical facies that are present in a water sample. But as you can see, it's not very easy to parse out these data and understand if there are any differences amongst the geochemical data. Most of the geochemical data are encompassed in this green box, but you can also see that there are a few outliers, including Saragossa and our sample from the volcanics in the Davis Mountains. However, we can use a combination of isotopes and statistics to better understand what these different sources may look like in the springs. So pictured here is a box plot of sulfate, which is a major anion for all 6 springs. That includes both the data that we collected in the field during our field campaigns, as well as previously collected data from other sources. And there are some general trends that we can start to see just by just by a simple box plot of this particular anion. Here we have Giffen, Phantom Lake, and San Solomon that have pretty similar mean values for this ion concentration. The Sandia is grouped together quite nicely as well. And Saragossa is kind of an outlier and doesn't really fit in within each category. And although I've only shown you sulfate, there are generally elevated ion concentrations for the Sandia springs across all ions that we evaluated in this framework. So moving forward to multivariate statistical analyses, there are two examples that I used in my work: principal component analysis and exploratory factor analysis. We don't really need to get into the nitty-gritty, but all I want you to really know is that both of these methods can provide clues to groupings using a smaller number of variables. This might enable simplified fingerprinting because disparate chemical elements are retained but combined into fewer variables. So let me show you. So here's the result of a factor analysis I did for our major ion data in our study area. And as you can see, much more effectively we can separate the ion chemistry, much more so than that Piper plot I showed you. Again, we see some clusters similar to the box plot. Giffen, Phantom Lake, and San Solomon group together quite nicely, as do the Sandia Springs. And Saragossa, again, is just very different. However, it just so happens that there are other clusters of data that are associated with specific conditions. There's another cluster of Giffen, Phantom Lake, and San Solomon data, pictured or circled in red, as well as an East Sandia subset of samples as well. And it just so happens that these chemistry data are associated with rain events that occurred in 1990 and 2004. And so for Giffen, Phantom Lake, and San Solomon, these ion compositions are much lower, which would make sense if you have much fresher water coming through the system. But for East Sandia, the ionic compositions are much higher. There are no available data for the other springs to evaluate how they may react or to such a rain event. But this behavior in itself does warrant additional sampling to figure out, is this persistent or just a fluke? Isotopes are another valuable way that we can start to look at the sort of fingerprints of these different waters and how we can better understand ages and sources of recharge. Isotopes of water include deuterium and oxygen-18, and these two isotopes of water act in a biased manner during hydrologic processes such as evaporation and condensation. And so the global meteoric waterline is an important trend that sort of represents how the average relationship between these two isotopes and meteoric waters. And it's really helpful to be able to ascertain sources of recharge and impacts from temperature, continental effects that were present at the time of recharge. This threshold, oxygen-18 at negative 7.5 per mil, is an established threshold from a recent study that basically helped us to define timing of recharge in this study area. Really, all I want you to take away from this is that oxygen-18 values greater than negative 7.5 per mil typically indicate local recharge. So think rainwater, modern water from the Holocene. Oxygen-18 values less than negative 7.5 per mil indicate submodern recharge. So these waters are thought to originate from the Pleistocene, so sometime 15,000 to 20,000 years ago during a cooler and wetter climatic period. And as you can see, there's clearly a segregation in our samples. Giffen, Phantom Lake, San Solomon, East Sandia, and West Sandia Springs are all characterized by this submodern recharge signal. So much older waters have a fingerprint or an imprint on these springs. However, Saragossa has a much more modern signal that is sort of coincident with modern rainfall as depicted here. Carbon isotopes are another valuable way that we can look at the age of groundwater or the evolution along flow paths. Carbon-14 can be used as an environmental tracer to determine the age of groundwater when it was taken out of contact with the atmosphere. For this graph, I just want you to take away that typically as you have smaller carbon-14 values, it's older. Differences in carbon-13 may be attributed to different lengths of groundwater flow, the type of flow path, or interactions of water with the aquifer matrix. And so as carbon-13 increases, it's typically older in this diagram. And so, as we might expect, there's a general decreasing trend in these carbon isotopic compositions, which pretty much leads us to believe that all of these spring samples are a part of the main flow path, or main flow system. However, there are a few differences that we may not expect. The carbon-14 signature for East Sandia, West Sandia, and the Pecos alluvium is a little bit higher than what we would expect for this respective carbon-13 value. In addition, there are again two subsets of Giffen, Phantom Lake, and San Solomon data in this system. And again, we see 1990 and 2004 rain events are clustered separately than our other geochemical data for these springs. And lastly, Saragossa Spring has a modern signal or a carbon-13 value that is closely associated to what we might expect in soils, and a very high percent modern carbon signal, which leads me to believe that there is a modern signal captured in Saragossa again. Okay, so we've collected our geochemical data, we've applied our multivariate statistics as well as our geochemical analyses, and now we get to the fun part, our refined conceptualization of this hydrologic system. So, isotopic compositions of the springs are consistent with a conceptual model of older groundwater from a regional flow system that upwells through carbonates and alluvial sediments to discharge at the springs. So as I showed you earlier, most of our springs have this submodern recharge signal in our water isotopes. And so what we can surmise from that is that this regional flow system previously established pretty much feeds all of the springs. In addition, elevated ion concentrations in carbon isotopes in East Sandia and West Sandia springs indicate the mixing of water, possibly by irrigation return flow or precipitation through alluvial sediments impacts flow at both spring outlets. Sort of this deviation from what we might expect for the carbon-13 values, this diluted signal in the Sandia springs, leads me to believe that there is some surficial component that is being added to provide local recharge to the Sandia springs. Irrigation return flow is a documented practice in this area, and what that really means is you're taking older water, possibly from the Edwards in this area, and using it as a source of irrigation, thereby providing, recircling older water through the system. In addition, Saragossa is likely a seepage spring and is more heavily influenced by a near-surface component. We saw again and again through our isotopes that Saragossa is the oddball in this sort of system. And so what that probably means is that this is a spring with a low flow rate. There may be a drainage-fed component in addition to a deeper underground source that contributes to flow at Saragossa Spring. And lastly, as I showed you many times, there's a subset of records for San Solomon, Phantom Lake, and Giffen Springs, which indicate lower ion concentrations, which ultimately suggests that there is precipitation is entering the regional system as local recharge. So as pictured here, we have this subset of geochemical data for Giffen, Phantom Lake, and San Solomon. What that likely means is that there is precipitation that enters Cretaceous outcrops in the region that ultimately feed the springs during rain events. And whether that feeds the smaller springs, such as West Sandia, East Sandia, and Saragossa, is something that needs to be evaluated moving forward. Okay, so what have we done? We've established and confirmed that there's a regional flow system and local flow paths that contribute to this multi-outlet spring system. The whole point of this exercise was to demonstrate that we have stronger evidence for these sources using robust geochemical data. And so as depicted, these sources of recharge span across multiple counties and jurisdictions. The challenge is that the source areas to this spring system are not entirely within a single jurisdiction. So these source areas do not honor political boundaries for jurisdictions to provide easier management of the spring system. So what that really means is Greg in Reeves County needs to be sending Christmas cards to those in Culberson County and Jeff Davis County to manage their water resources to not deplete the springs. And so this geochemical framework has broad applications to the analysis of groundwater problems in areas of increasing limited water availability, water resource assessment in complex geologic environments, as well as being able to identify sources of anthropogenic activities. So to summarize, geochemical signatures of groundwater can be used as indicators of different components of flow to the springs and can be especially useful in characterizing different sources that contribute to multi-outlet spring systems. San Solomon Springs is in Trans-Pecos, Texas, and it provides an example of a multi-outlet, multi-source spring system. And there are 4 different flow components, both local and regional, that are elucidated by this geochemical framework that contribute to this spring system. I'd like to acknowledge a number of groups and people that made this work possible. Namely, Big Bend Conservation Alliance really got us started in the area in 2019 and helped us to get our feet on the ground and start looking at this spring system and the geochemistry. Southwest Research Institute provided internal research funding to also allow us to keep working in this area. Chad Norris, Ryan Smith, Greg Perrin, Abel Baeza, and Ty Edwards were all instrumental in helping us to access the springs, which was, of course, an integral part of this project. And with that being said, I've included my contact information because I'd love to talk to you more about this if you have any questions or if you'd like to read any reports or my thesis regarding this area. But with all that being said, I'd love to take any questions you might have. Thank you. It just provides justification for, or not justification, it just helps to elucidate how water is getting into this system. So large rain events that are occurring in the area are going to enter the system rapidly to feed spring discharge. And so it's affecting the chemistry in a way differently at different springs, but nonetheless, it's just elucidating that rainfall is going to meet the springs. So the geochemistry is just a really important, powerful way of identifying the different sources that may contribute to this spring system. And what I hope this will provide those that are generating numerical models or are involved in model development is a way to better constrain their models to evaluate how pumping might impact spring flow or where certain areas are they're impacted, how they may ultimately impact the springs. So it's really helpful for model development. If you recall, there was a white zone when I pictured the GCDs in the area. I mean, it sort of elucidates that there is this unmanaged area. I believe there was a ranch purchased in this area for $500 million that's going to, has purchased the water rights in this area. Well, what does that mean in water management and how they impact the springs? Well, By the application of this geochemical framework, we've shown that these large regional flow paths intersect these areas of development and may impact the springs. So really it's just meant to provide those that are managing the springs, are involved in establishing DFCs, the areas to look at when, putting forth policy to protect these water resources. I don't have that on hand, but it's a fairly low flow discharge rate. It's a great question, and I will look into that. What's the flow rate at Saragossa? Very low. Very low. Right. Right. Sure. So I definitely took regional chemistry into consideration, and one of the things that I didn't include in this presentation but was a pretty strong point of evidence for establishing that this regional flow system meets all of the springs is strontium isotopes. Strontium isotopes are very helpful because they sort of retain the signature of different geologic environments because they don't fractionate. And so there's not a lot of data in that area, especially with the robust suite of analytes that I used. But what was really helpful is that all of the springs have a very high value in strontium isotopic compositions that ties quite well with this Wild Horse Flat, western Culberson County region. So, if we had more time and money, more data, we would have been sampling all along, Culberson County, along these regional flow paths to better constrain, the chemistry in these recharge areas. But I had to rely heavily on literature values and the previous work of others in the area to sort of pinpoint how the chemistry ties in with the springs. Yes, absolutely. We have a few things in the works to potentially gather a lot more geochemical data in this region. Ideally, we'd like to sample more in Culberson County, but there are a lot of issues with private land access. I'm sure others are aware of that difficulty in the area. But another thing we're looking at is sort of expanding our geographical scope to include the area between San Solomon and Comanche Springs, as these flow paths are all interconnected. Ideally, I'd get to sample all the way from Culberson County, the irrigation water in Balmorhea, all the way down to Fort Stockton, but it's to be determined. Sure. Yeah, no, that's a great recommendation, and that's something that me and my colleagues at Southwest Research have talked about doing. From a quantitative side, we are not really involved in the numerical model development, although that would be a great endeavor to embark on. But geochemical modeling, such as mixing models and equilibrium, reaction path modeling, I think would provide a better quantitative metric to ascertain, these, origins of recharge to the springs. And that's just something that we're looking into moving forward. Thank you for your question.